research team lead at the USC Information Science Institute. There's a fun fact that Professor Ren was an intern at Pinterest during his PhD study. And he actually worked on the early version of our interest taxonomy project. So yeah, welcome, Professor Ren. Mm-hmm.
Thanks for having me here. I noticed that I'm the only academia person in this group, and that actually makes this very interesting kind of let's say environment for me to share things, because I even though I've been doing research, I'm also kind of caring a lot about what practitioners think about the work we are doing. And also I did have a little bit industry experiences, both in during the time of my PhD and also when I'm starting at USC. I also was part-time spending some time at Snapchat working with their data scientists people and try to help with their products in some extent. So the one topic I feel like really suitable for today's kind of a sharing is this how to make this knowledge graph construction, or let's say some of these technical problems we are facing, like entity extractions, relation extractions, or other, let's say, classification problems, to be more adapted to changes of, let's say, requirements. For example, that could be referring to you are dealing with some types of entities day one, but then in day 7, you are asked to dealing with some different set of type of entities. All your data distributions change a lot because you, I don't know, there's some different things happen to your data pipeline. You start accepting some new data, which looks rather different from before. So yeah, that's about a fast aspect. And the faithful aspect, I think, might not be studied that much in the industry setting. But I think right now what we really find out is there's some really powerful models we've been using in, let's say, natural language processing community or machine learning community, and they perform really well on some of these benchmarks data sets. But what really those models are learning is some kind of spiral patterns, which could lead to good prediction results, but it's not really generalizable and could have some ethic issues. Okay, so yeah, before I start, I just want to thank my students of pretty much done all of the work here. And I have been collaborating with folks from different places and getting supported from different agencies. Right. So I want to start with just kind of having my personal type of overview of what is really happening, let's say, in knowledge graph construction in terms of the academia research, or more broadly, the natural language processing research. So we've been kind of seeing a convergence to a general recipe of doing different information extraction tasks or knowledge graph construction tasks. The recipe basically consists of 3 parts. One is the model architectures. Right now, we are more talking about some sort of neural model architectures. And there's this label data, which you use to learn the model towards your end task. And then with sufficient computing power to make sure you can do these things even offline with some time constraint, you can do this in time. And what is really happening right now is the model architectures become a sort of commonalities where you, let's say if you're using Hugging Face libraries, then it's just 2 lines of codes. You can import a model architecture. And if the other day there's a new model architectures being put into there and you find it's more superior, you can just switch that by just changing 1 line of code. Things about computing power is also pretty much similar. At least if you, I mean, different companies, of course, have different practices. But let's say if you're using some third-party cloud services and using their GPU computing powers, then it's also just changing a line of code. You can use some better GPUs. So what is really remains as the question is, where do we get the label data for my problem? Or even you are solving the same task, where can I get new label data when my data change a bit, or when the labeling requirements change a bit. So I think this is kind of the part that my research agenda is really want to make some progress. We are trying to think about in the scenario where the label data is really adapted to different tasks, and how can we get the label data, or how can we supervise these models for knowledge graph construction in a much faster paced, right? Just to give you a sense of how expensive collecting label data is, I think this was the slides I usually use to motivate this talk towards the more academic audience, but I guess I don't need to emphasize too much about this towards practitioners. Most of you probably know that you have maybe your in-house crowdsourcing service, or you're using some third-party crowdsourcing services, and even designing a smart way to solicit this label data is by itself kind of challenging problem. So we have this like TechRed data sets, which is the largest one for relation extraction task out there as a public resource. And it consists of like about 100K sentences annotated for 40 relationships. And even just for creating these data sets, roughly estimated it would just take more than a week and about $50K dollars to really do this in a kind of a reasonable way. And of course, this cost is really linear, proportional to the scale of the data sets you need. And it's also depending on the complexity of the task. So relation extraction is not really that complicated task where you just need to go read through one sentence and think about what is the relation type that was expressed between a pair of entity spans. For example, in this case, is this beauty maids and Tampa. And then the relationship should be annotated as like, this is the place that this person that. Yeah, so this is actually a pretty simple task, or let's call a lower level task in terms of the entire knowledge graph construction pipeline, but it's already pretty expensive to create data. And of course, in academia, there's lines of work trying to say, I'm gonna help you reduce this reliance on label data when you adapt into new domain, which in other words, trying to accelerate your training or learning process. So there's this multitask learning, transfer learning, active learning, and also this distance supervision concepts. But the problem we see is that they have pretty strong assumptions on, let's say if you have some source data, you do have lots of label data on the source data, and you have a new domain you want to adapt to where you have very limited label data, or it's expensive to get a larger amount of label data there. You can try to say, I'm gonna learn this task over these two domains jointly, or I can transfer from source domain to the target domain, or something else. But there's a very strong assumption on how close these two data partitions look alike to each other. And if there's not sufficient similarity between these two domains, all these methods I'm just talking about here probably will fail and might not work, and even might hurt your performance. Yeah, so what we've been thinking as an alternative in our research agenda is this idea of, in addition to just creating label data, like given a sentence, I annotate the entity spans over the sentence, or I annotate the relations between the pair of entities, or something else like sentiments of the sentence, any task, any subtask you can think of under this knowledge graph construction pipeline. We are thinking about, can we provide a way to solicit users' explanations about their annotations? And we want to provide methods that can make use of these human explanations about their annotation process, such that the learning can be much faster than before. So this is really a good an analogy to humans' learning process. So you are provided with, or you always be provided with a few examples for the concepts you are learning. And you might start making mistakes when you try to generalize to new scenarios because you only see a few examples. But then you will actually get corrections in the form of maybe natural language explanations, or in the form of more examples to correct or rectify your behavior, and you do this back and forth, and you start learning much faster. So we are kind of like inspired by this process and trying to really want to model this type of explanation. For example, if you tell me that this person and this coach is the coach of this team, and the reason that you annotated this person is the coach of the team is because you see the phrase coach occur between the subject and the object of the sentence. That's a very good clue for me to learn about why you make such an annotation. And more importantly, this clue can be used towards many more other sentences with similar sentence structures. And even though those sentences are talking about different person and different teams, sport teams, I can still try to classify the pair of those pair of entities as coach of certain team, right? So there's this generalization power that I'm going to talk about. So I don't have too much time, so I would just quickly skip through a few questions we posed when we think about this learning from human explanations, and just give you a sense of how we are trying to approach those problems. So we start with thinking about, let's say we are not provided with these natural language sentences as explanations, but more like regular expression patterns, those more structured rules. How can we make use of them? And then we'll move on to say, how can I digest even just very natural language form of explanations? And then I would just switch gear a little bit and just talk about how we can make use of this knowledge as sort of inductive bias to help answer questions. So these are kind of very new work. I don't really have a product to talk about like the previous speakers. So I'm just trying to say if I can just talk a little bit about this new work and see if we can find any good use cases by the discussions later on. So standard pipeline for data annotation, as most of you have been familiar with, is like annotator is presented with a bunch of instances, and then they just read through each of them and trying to give the label, right? And those labels throw into the downstream machine learning pipelines. In our case, we've been thinking about some kind of neural network classifier. So this is slow because there's too much redundancy in the annotation. All of these sentences shown here is just describing the relationship between this person and a company is founded by relations, and they all have very similar context or language structure, which is kind of anchored by this phrase was founded by. But you need to annotate them 3 times. So you are actually wasting a bit of time. The idea to improve over that is just to say, can we come up with patterns instead of reading individual instances one by one? For example, I think Hertz in even 90s, she proposed this idea of writing down some rules like subject organization was founded by object person will lead to the annotation of the relationship should be founded by. And these rules can be applied to all of these 3 sentences and get the label. So that seems to be better, right? The problem is language is so diverse, and there's so many ways to express the same meaning between a person and the company, which can be still talking about founded by relations, right? You can use the phrase like was established by or launched, anything like that. And this single rule we just see would not generalize to those, right? So they will fail, they would not match. So if we're talking about exact matchings, this won't work. So our idea is, can we do a sort of soft matching or fuzzy matching? So it seems pretty straightforward, but I mean, there's not really much work that can do that in a both effective and scalable way. So my student Renshen has this like actual best paper running up in this year's conference, the web conference. The idea is pretty simple. It's just saying, in addition to the hard matching that we just talked about, we can do a sort of a soft matching, providing X, Y, which is the instance label pair together with some kind of confidence score, matching score. And together, these 2 subset of label instances will be used to learn the model, the relation classifier, for example. This idea doesn't just work for relation extraction, it can also work for sentiment classifications, entity classifications, things like that. right? And a good benefit of this approach is you really understand what is the model doing. So you know the rule is matched to a certain sentence because certain words in across these rules and the sentence are close to each other in the semantics. So you can use this heat map to understand what is really happening between the during the soft matching process. And just quickly show the results. The two curves in the middle of the chart is just showing that annotating rules and annotating instance have pretty similar time efficiency. It's just only a small, yeah, there's only small gap here. But the performance you get from using the rules, which is the upper blue one, is much, much better than using only the annotated sentence. So I'm gonna skip this part quickly. So the next step we've been looking at right now, it's still ongoing, but we have some results already, is to just take in human explanations about their decision process and trying to directly model this. Just to give you two examples, if you are concerned of sentiment analysis, there will be like, hey, this sentence should be annotated as positive because I saw the words very nice is within 3 words after the entity spans. Let's say you know where the entity span is, assuming you already run the NER pipeline, right? Or if you're doing relation extraction, you can say, hey, I think this person and this entity, one entity you have the relation is like the nationality of the person because I see the words is a appear right before this entity span, and the other word citizen is right after the other entity span, right? Something like that. So this is just giving you a very high level idea. So what we're really doing is, I'm not gonna talk about these details, is we can translate these explanations into a sort of a program, which is executable over other instances. So that means you have explanation at hand, you can see if the explanations can explain other new instances where it's not written over. And that's a sort of a generalization. For example, you can say, I classify this sentence as positive because the word price is preceded by the word fair, right? So you have this fair price kind of pattern. And you can also use that to find out the other sentence, it has delicious food with a fair price, is also a positive sentiment because you see these explanations can apply to there, or a hard match. Similarly, we can do hard match together with the soft match I just talked about. I'm gonna skip this part for the interest of time. Again, we see a huge improvement on the performance when using explanation in addition to the label data, compared to only using the label data here. That's the gap between the blue one and the rest of the curve here. I mean, the numbers here really seems very low for the production quality. So I mean, this is just like a kind of a proof of concept type of experiment. So just 3 more slides to go for this third piece of work. In here, we actually are pretty interested in the type of question answering where it clearly require external knowledge. Questions like, where do adults usually use glue sticks? And you have some answer choices, or you can just give me any answer concepts you can think of. So to answer these type of questions, you really need to understand a lot of things, like adults locate more often to locate in office than in classroom. Glue sticks can be located in classroom, office, and desk drawer. And then you make all these conjunction and multi-hop reasoning, you come to the most plausible answer, which is the office, not the classroom, right? Similarly, as like what do you need to fill with ink to write notes on A4 paper? There's lots of possible. There's many things behind the scene that is going on. Like, you know, to write on A4 paper, you need something that is functionality of writing, and all of these 3 can do that. But only the fountain pen and printer need to be filled with ink. And also, you know, A4 paper is more likely to be used with printer. So actually, there's no definite answer here, but there's only more plausible answer here. So the idea we have here is really, how can we think about which subset of the knowledge graph that you are hosting can be useful to the current questions you are asking, and you're trying to you retrieve those pieces of facts and put them together to try to answer this question. Right. So in the same example, we see from Concept Lab, this knowledge graph, we can find out that office the work can happen in office. Adult is capable of working. Adult is capable of using, and glue sticks can be used, and then glue sticks can locate it at office. All of these things together can help you identify office as more plausible answer. So this is sort of a neurosymbolic reasoning process that we are pushing for in our research agenda. And that is all I want to just share. We also have a bunch of other work that trying to use distance supervision to help knowledge graph construction and also reasoning over knowledge graph. All of the manual, I think most of this work we talked about today are open source on GitHub. I'm happy to talk more if you're interested in trying some of them in your own products. Thank you.
Thanks, Professor Ren. And the presentation is very inspiring. So any questions? Mike?
So I love this data augmentation work. I'm wondering how your approach is similar to or different from Snorkel.
Good question.
That Chris Ray came up with.
I know Chris is super popular in Bay Area, so he probably give talk in every single company. So there's a few key distinctions between our line of work and Snorkel. One is Snorkel is still, let me try to see if I can just stop at one slide. Yeah, maybe this one. So you guys know that Snorkel is asking users to put, input is sort of what they call labeling functions. Right. And this really means like you need to understand sort of the grammar and or like the format of the programming languages they are using. And this is actually too much ask for a domain expert. If you really want to make this platform powerful to accept human explanations, you should more thinking about what is the domain experts, which might be non-CS professionals, can be providing to you in a smooth and easy way. And that's actually a big motivation for why we want to deal with human natural language type of explanation. Of course. And the second big difference is that Snorkel is most, I think at the time, I think I'm still tracking what they are doing, but right now they probably are not disclosing all of the details of their products after acquired. At the time when
they got bought by Apple.
Yeah, at the time when I know they are not doing anything beyond hard matching. So every labeling functions or programs they produce will be doing exact match to the data points, which have pretty limited coverage.
They went on to do distance supervision kinds of things as well.
Yeah, the distance supervision is in my understanding, is part of the labeling function, because if you have a fact in a knowledge base, you can apply the fact to many new sentences where you see the entity occur. So that's the distance supervision. But that kind of rules is using exact matching. So only if the entities spans can match to the sentence spans exactly, you will say this is a match. And that will lead to very limited and biased coverage of the matching process. Yeah. So that's also why we are, I didn't actually include those technical details, but the soft matching, it's a major technical innovation compared to Snorkel. So I would say like interface-wise, human explanation, it's a very important thing to make it easy to use by domain experts. Technically, is soft matching, make it more, have a higher coverage in terms of the matching results. So you will have more label data.
Yeah. So one last observation. This seems very closely related to the things I'm seeing called instructability. So it's as if you're instructing the program how to proceed with additional examples. Do you see a link there?
Oh, thanks for bringing this term. This is actually the first time I heard of this term, instructability. Okay. Is it like a term from the education domain, or
no? No, it's a kind of conversational interface for what would you say? For updating data, for example, that's one use case. So it's a kind of a conversational front end for doing these kinds of things.
Yeah. Okay. If
you ping me offline, I'll show you where I saw it.
Cool. Sounds great. Yeah. Yeah. I like to know some pointers or references. I think one part I know is at Microsoft there's a team called Machine Teaching Team.
Yes, I'm very familiar with them. Yeah.
Yeah, they are doing.
Right.
But I know they are more caring about its user interface, the HCI part of it. But I think the kind of the high level idea are kind of pretty much sure. Like they want to really teach machines about the rationales behind doing things rather than just providing them labeled data.
Exactly.
Where the models are super easy to learn spiral patterns when you're only providing label data. They can learn things like, because I see these prepositions, because I see this determiner, right? Or I see these small symbols in the sentence, I will classify them as something. But that's not really what the people, the human, want the models to catch up. Yeah.
Right.
Okay. Any other question?
So one question, Xiang, this is awesome. I'm wondering, with a typical human judge task, right? For one particular item, we may ask 2 or 3 judges, right, to judge on the same thing, right? And then you try to come to a consensus, right? Do you see similar approach applicable here?
That's a good question. I think when people are asked to write explanations, there might be so I think these two things are very complementary to each other. When there's a divergence between the annotators on the annotation results, understanding the rationales behind each individual annotator is actually a very good thing to see what is really happening. Maybe they are sharing very much the same rationale, but they just have a very subtle difference on the features they are capturing. And that leads to different predictions. And that will help the engineers or the managers to understand maybe the problem, the instructions of my annotation process is not well defined or something like that, right? Maybe the problem is not about annotators themselves, it's about your instruction or your definition of your schema. It's not that easy to understand by people, so they have misperception, things like that. So I see this explanation might also be possible to use to give feedbacks on the annotation instructions and guidelines than task.
Right.
Yeah.
Makes sense. Yeah.
Another thing that I found related to that is that it's often more informative if we don't ask for Boolean responses, right? This is an example of this. If you ask for is this a cat, or how likely is this to be a cat? So instead of a Boolean response, we have a graded response. I found that to be much more useful along the lines of what you're doing here. Instead of a Boolean, is this true or false? You're saying, oh, what's an explanation?
Right. Exactly. Yeah.
Good.
Okay. All right, Xiang, I have a quick question. So the augmentation is really a great way to collect training data. I think it's super practical for industry. So I wonder, why didn't you use the mechanism of, like, say, let the annotator annotate like a seed list, then create some rules. So, for example, the company is funded by somebody. That example, if we have a small set, you can maybe learn multiple rules. Then we can validate the rules, say, oh, 3 rules apply. X is founded by Y, Y founded X, and X is established by Y, right? So then kind of do some iterative process to collect multiple rules, then to improve overall quality by just using a hard match. So why did you go with the soft match route instead of this?
Yeah, I think, yeah, I mean, again, I think there's this intentions of the academia want to make the approach and problem clean, but doesn't mean like I think in practice, I actually pretty much agree with the procedures you just say. And it's actually, in fact, also how we did experiments. We are not coming up with those rules. We are not asking the annotator to come up with those rules from scratch. We actually present them with a bunch of candidate rules. and they just need to go through those rules and say, this is a good one, I agree with, this is not a good one, I will use. So they really don't need to spend time to be so creative to write down rules one by one. And those candidate rules can be seen as generated from the seeds examples that you talk about, right? I can look at the C examples, I can look at the sentence they are in, I can find out some rules, and then I can present this to the users, and then they do a round of verification, and I can do this back and forth, and to get more and more rules. I see this as actually what in practice can be applied.
Okay.
So just an extra point there. So the hard matches are really difficult. When I was at eBay, I studied buyer and seller emails to see how many different ways they could say something like, can I pay with PayPal? Okay. And I found for a simple sentence like that, that there were more than 20,000 variations.
Really?
So we can't, at that scale, we can't use regex or hard matching or anything like that. The scale is very, very big of a variation.
Yeah, that's a very good point. All right, thanks. I think we can discuss more in the roundtable session. All right, thanks, Professor Ren. So we're a little behind schedule. So instead, let's shorten the break time a little bit. Instead of 20 minutes, let's do 15. Then so let's come back at, that's actually 18. Let's start the roundtable at 11:30. And we probably want to shorten the roundtable a little bit as well.